Hello and welcome to the second half of Lecture 15. Here we're going to get into Chapter 23, 23, and we're going to cover images formed by mirrors. So let me make a quick correction here to my heading where it should say 20, not 33. All right. So 23.1 and 23.2. All right, so these are images formed by mirrors. We're going to be talking quite a bit about images formed by optical devices, mirrors, and lenses. That's going to be a big focus of chapter 23. And so in doing so, we want to kind of lay the groundwork of learning the key terms of image formation, because there's a kind of a bit of kind of upfront knowledge that will apply to everything we do, talking about images, including images for optical devices that include more than one lens, namely telescopes and microscopes, simple telescopes and simple microscopes. And then we want to understand why planar, spherical, concave, and spherically convex, why planar, spherically concave, and spherically convex mirrors form images of different kinds. Okay, and and to do that, we're going to employ drawing rays, so rays of light, kind of following them in the same way that we drew rays of light that were refracted. And so then we're also going to develop a kind of a key equation that's based on that idea of light. In this case, everything is about reflection, so there's going to be no refraction in the discussion of mirrors, because we're not talking about light passing through something, but instead light just bouncing off of a surface. So let's start by getting some of those key terms out of the way. So the first key term that I want to introduce is something called a real image. Okay, so a real image is an image formed by light passing through a point. Okay, so this is an image formed at a location where light is present. Real images would be the type of image that could be seen on a screen, or could activate a photograph, so like photoactive paper. So they would be visible on a screen or activate photoactive paper, like a Polaroid. Now, interestingly about real images is they're invisible to the human eye. So I want to make two more points here. Is they're invisible to the human eye. And mirrors do not form them. So for now, we're not really going to have anything else to say about real images. We will come back to them when we talk about lenses. But for now, we're not going to see any real images in our discussion of mirrors. So on to the other type of image there's only two types of images, real and virtual. So virtual images are an image formed at a location where diverging rays appear to converge. Okay? So there's no actual light at the location of a virtual image. It's just it's just the projection, the continuation of diverging rays. And that's something we'll see quite a bit of, diverging and converging rays. And a ray just being that line that represents light, like we were doing for refracted light with Snell's law. And virtual images are the only type of image that can be seen by the human eye. So visible to human eye. And I know that seems strange at first, that the human eye can only see virtual images and can't see real images. And that's just due to the fact that our eye has its own lens. And so we can cause diverging rays to focus on our retina, and that's what we see. But we never actually see the location where light has already converged at a single point, because there would be nothing for the lens of our eye to do with that light that has already been focused at a single point. Okay. So then the three types of mirrors are our next idea, and that's going to be plane mirrors, convex mirrors, and concave mirrors. So a plane mirror is a flat mirror with no curvature. And this type of mirror is then it forms a virtual image that is equal distance behind the mirror as the object is in front of the mirror. So forms a virtual image behind the mirror. And the equal distance part I will call attention to in the formula below. The two types of curved mirrors are convex and concave. So a convex mirror is a mirror that curves inwards. All right. So, I meant outwards. Concave is inwards. So, mirror curved outwards. Okay. And so this type of mirror also can only form virtual images. So it forms virtual images. And that have magnification set by object distance and focal length. That would be focal length of the mirror. So important thing about convex and concave mirrors is everything that they do is set by their focal length. The focal length is the one number that you need in order to know everything about that mirror. You then can know the location of any of the images, what type of magnification to expect, as long as you know the focal length. Okay? Now for the concave mirror, we have this is a mirror that's curved inwards. This type of mirror can form both real and virtual images. Okay, so this is the only type of mirror that can form real images. Which makes me realize that I misspoke a minute ago. I was so focused on planar mirrors that I failed to remember that, of course, concave mirrors can form real images. So we actually are going to be talking about real images, which is a good thing I brought them up. So this is a point. This would be an image that we wouldn't see. So if you were standing in front of a concave mirror at the right distance in order to form a real image, you would see no reflection in the mirror, because what would be happening then is that all that light would actually be converging at a single point, that you would have to then put a screen there or something in order to see it, or a Polaroid. Okay, so please excuse my mistake from before. Concave mirrors can in fact form real images. They're the only ones. Okay, and whether they form real images or virtual images is going to be set by the object distance and the focal length. So we can say depending on the object distance and focal length. Okay. And then I'm going to illustrate this with the two figures to the side that I haven't drawn on yet. But I'm going to illustrate what the principal rays are. So there's three principal rays, and these are used for figuring out where our images are located, which we can confirm with a formula. So we do have a formula. We don't have to draw figures every time we solve a problem that has a mirror. But often the drawing really gives us an expectation. It's really important in the same way that a free body diagram is so useful in solving a force problem. Even though technically we could just do it all with the equations, the figure is a guiding tool. So 3 principal rays. And what are they? So principal ray number 1 is a ray that passes through the center of the mirror and the optical axis. Look at the figures to the side to see the optical axis. Okay, principal ray number 2. So this is a ray that is parallel to the optical axis on incidence. So parallel to optical axis on incidence. Okay, so that's before it contacts the mirror, and it passes through the focal point. Okay, looks good. And the third and final of the principal rays, and more on the focal point in just a minute, is a principal ray that passes through the focal point on incidence. Okay. And so here I'll clarify here, instead of saying passes through, I'll say reflected through the focal point. All right, looks good. The only issue there is that sometimes it's not literally reflected to the focal point. It's a projection of the divergent ray that's reflected to the focal point, but they'll become increasingly clear. Because what we definitely have to do with these 3 principal rays is draw examples of them in the diagrams that I've included. Okay, so I'm going to do it in both cases. All right, so we'll start with the convex mirror. So mirror number 1, this is the curved outwards mirror. And I'm going to put an object on the optical axis. You could think of this as some sort of just demonstration object. I'm going to draw it as an arrow. So it could just be a ruler, for example, that you place in front of the mirror. Okay, so here will be our object. Okay, and then I'm going to choose one point on the object, the top, and I'm going to draw the 3 principal rays coming from that single point. Okay, so principal ray number 1 is the one that passes through the center of the mirror. Okay, so this one then will come down like so, reach that point where the optical axis meets the center of the mirror, and then due to the law of reflection, then it's going to come right back off at that same angle. Okay, so the idea there is that theta 1 equals theta 2. Okay, so that is our first of our principal rays, ray number 1. Okay, now let's draw the second one. The second one is the one that needs to be parallel to the optical axis upon incidence, and then it's reflected through the focal point. Now, however, for convex mirrors, we see the focal point is behind the mirror. So it only is going to be a continuation of the ray that is reflected to the focal point. So it'll look like this. So first of all, parallel to the optical axis. Then let's think about what's going on. Now it's going to get reflected like this. There. Okay. So I've drawn it in this way to show that here there's actually no light. So here we're going to have a dotted line to indicate that there's no actual light passing into the mirror. All the light is reflected off the mirror. But this is a continuation of that divergent ray. And by doing that, then we can clearly see the direction that this particular principal ray 2, travels. Okay, so that would be 2. Now, obviously, if we had a different size object, Like if it was taller, then the principal ray would come in higher up, and so then it would then have a different angle, right? So you get reflected at a different angle. So the height matters. Also, if we brought our object in closer, then our second principal ray would come in, would get continued down to the focal point at a different angle, and so then it will get reflected at a different angle. So the location of the object, our pink object here, and the size of the object both matter. Okay, let's do our third and final principal ray. This is the one that is going to pass through the focal point. Okay, again, for the concave mirror, it can't literally pass through the focal point because the focal point is behind the mirror, but we'll draw it in the way that it would had it not been reflected. Had the mirror not gotten in the way, right? So it would look like this. Yeah, that's pretty good. Maybe I try drawing it a little bit better. Yeah, being picky. Okay, that's fine. Okay, and we can erase the end of it at least. Okay, so then it's the idea, right? So over here, on this side, there's no actual light. So that's just like principal ray 2. So I'll make that a dotted line. But then I need to have it get reflected. Well, here's the thing. If it was going to pass through the focal point, then we know it's going to get reflected exactly horizontal. In other words, it's going to get reflected exactly parallel to the optical axis. In the same way that principal ray 2 came in exactly parallel to the optical axis and got reflected along a line that passed through F, if the ray comes in passing through F, then it gets reflected horizontally. So they're kind of reciprocals of each other or inverses of each other. Okay, so we'll have this one come out horizontally like so. Almost. There. Okay, and so that's going to be our third and final principal ray. So they're there. So what's the purpose of these principal rays? Well, the purpose of them is to have a point where all three of them cross, okay? And so where are they crossing? Like where are they coming together? So, well, here's the thing. Right now it doesn't look like they're crossing, right? Because my dotted lines are kind of serving different purposes. So one thing that I'm going to do, because there's the two types of dotted lines, is I'm going to draw one as a dashed line and the other one is literally a dotted line. And I'm going to explain kind of what different purposes they serve. Okay, so zoom in a bit more on this. So the one that I'm going to redraw is the last one I did. That's principal ray 3. And the only reason I'm going to do that is because I want to show that there the dotted line represents the incident projection rather than the reflected, well, I should say the incident continuation rather than the reflected continuation. Okay, and do know that I'll elaborate on that. So here, I use this line in order to know which way to draw the ray coming in. And that was important because I needed to know where it hit the mirror to draw that horizontal reflected ray. Okay? However, this one here, this dashed line, represents a continuation of the reflected ray. Okay? So I bring that up because now I'm going to take the incident ray, or rather the reflected ray for principal ray number 3, and I'll draw that continued back into the mirror as well. But I'll draw that one dashed. So this one comes back into the mirror like this. Okay? So this dashed one here is a continuation of principal ray 2. This dashed ray is a continuation of principal ray 3. Both being continuations of the reflected ray, because it's only the reflected ray that the human eye is going to actually be able to see, because our eye is taking that in, taking in that all those divergent rays, and then continuing them to a point where the image appears to be located. It's like our brain is processing that information. It's saying, okay, well, all these rays are coming at different angles. What does that tell us? That tells us that there must be something where they converge. Even if they're converging behind a wall, our brain still says, well, there's an object there. Okay, or there's an image of an object. So likewise, we'll take a continuation of ray 3, principal ray 1, and we'll bring that back into the figure as well as a dashed line. Okay, so that's the continuation of reflected principal ray 3. So now we can clearly see there is a point where all three of those continuations cross over each other, and that would be the location of the top of the image. So we'd have an image that would look like this, like so. Okay, so that is our image for this concave mirror. And we call it a spherical concave mirror because this focal point is 1/2 the radius. Okay. So the focal length is 1/2 the radius of curvature. Okay? And the focal length, as you might be like, well, f is just a point. What's the focal length? Well, the focal length is the distance from the center of the mirror, or in other words, it's the distance it's a distance from the surface of the mirror along the optical axis to the focal point. So it would be this distance right here. So that is what we call the focal length. Okay, and we use f for both. So f for the focal length, f for the focal point. Because ultimately this is kind of this point right here is the origin, and so it's just the coordinates of the focal point is the focal length. Okay, and so that means that C right here is the center of curvature, which is the radius. The center of the circle. Okay, so there we have it, concave mirrors. Concave mirrors are a little strange because of the way we have to have all those rays going back inside the mirror. So drawing them required a little bit of explanation in that regard. But the thing that's simple about them is that they always create virtual images, so they're more similar to a planar mirror in that respect. Okay? The type of mirror you'd have in your bathroom, for example. But what's going on with a, well, concave spherical mirror? Well, here we have a case where we can create both types. And I'm going to show you a real image for an example that includes our principal rays. Okay, so let's go ahead and do that. So we'll have our pink object. So I'm going to put it over here. All right, and then we'll draw our 3 principal rays. 1, 2, and 3. All right, so let's just go through them at a quicker pace. Okay, so here's principal ray 1. That's just following the law of reflection. And then I'll have principal ray 2. Okay. So you can see this one, I didn't have to do any continuations of the ray inside the mirror because in order to pass through the focal point, it is just going to do that naturally because here the focal point is outside of the mirror. And quick note here, right? Do notice that for the concave mirror, the focal point is defined inside the mirror by definition. For the convex mirror, the focal point is defined inside the mirror by definition. For the concave mirror, the focal point is defined outside the mirror on the same side as the object. Okay? And that's kind of has important consequences about what we call a negative focal point and what we call a positive focal point. Okay, and I'll call attention to that because it's really important to pay attention to the conventions about sign, especially when we're using these formulas down below. Okay, but let's wrap up this figure in the interest of time. So we have our third and final of our rays, and this is the one that's going to pass through F. So let's get that. Pass through F at least on incidence, and then upon reflection, it should be horizontal. So it needs to kind of come down a bit more. It's quite steep enough. Me. Okay, close enough. All right, and then upon reflection, it'll look like that. You can see, they don't come out perfect when you draw them. It's actually easier to draw with a ruler by hand than with the computer here, with the tablet. And so then we have, that's number 3. Here I wasn't labeling them all that well. So this one here would be number 2. This one would be number 3. They're kind of all overlapping each other. But then we can see that we end up with an image that is down here. Okay, so that's our image. So let's think about this. What's going on, right? Well, in this case, our image is on the same side as our object, and our image is at a point where light is actually passing through it. So this represents a real image, whereas the image for the convex mirror was virtual. Notice that the virtual image is not vertically inverted, it's upright. Whereas the image for the real image, the image for the concave mirror, is inverted. It's flipped upside down. Well, that's a rule. Virtual images are always upright. Real images are always inverted. Okay? All right. So let's put this all in the language of a formula. Now this is the spherical mirror formula. Okay? So the first formula is the planar mirror formula. And that one simply tells us that 1 over s plus 1 over s prime equals 0. Well, what are s prime? What does this all mean? Okay? So first of all, this is the formula for planar mirrors. Okay? So s is the distance from the mirror of the object. So s is the object distance. So using the concave mirror as an example, s would be this distance here. Okay, so this right here would be s. Whereas s prime is the distance of the image. So it's the distance from the mirror to the image. So image distance. So in the case of the concave mirror, we have our real image, and then that real image is going to be located at s prime. Like so. So that one is s prime. Okay? So then looking at this, then for the planar mirror, our 1 over s plus our 1 over s prime are equal to 0. So then if we actually then were to solve, the only way that this equation is true is if s prime equals s. Okay? So we see then for planar mirrors, there's a very simple result. S equals s prime. The image is always equal distance behind the mirror as the object is in front of the mirror. That also means that magnification is always 1, because magnification is defined always as negative s prime over s. More on the negative in just a second. Okay, but here then, because we have an s prime and an s, we end up with a value of positive 1. Well, why positive 1? Well, because s prime is by definition negative if the image is behind the mirror. Or the best way to say it, and this will be universal, and we'll be able to apply the same logic to lenses, is s prime, the distance of the image, is negative if it's on the opposite side as the object. Okay? So that means it's positive if it's on the same side as s. Okay, so let's make a note then. S prime is positive if on same side of mirror as S. Case in point, our concave mirror that forms a real image. In that case, S and S prime are both on the same side of the mirror, and so in that case, S prime would be positive. But S prime is negative by definition if it's on the opposite side. Okay, that's a rule you have to remember. And there's a consequence to that rule. Namely, that when you look at magnification and you have a magnification like the planar mirror, which is +1, that tells you that your image is upright and virtual. Because if your magnification is positive, then there's no inversion. Okay? So positive magnification means upright image. Case in point, the convex mirror with its virtual upright image. Okay? But when I say upright, obviously I also mean virtual. Okay? So upright is synonymous with virtual. Virtual. If the image is upright, it is virtual. If it's inverted, it is real. Okay? All right. So let's think about this then. So we just have a couple of last things to label. So he gave the convention about the S prime and when it's positive, when it's negative. What magnification or what positive magnification and negative magnification mean as well. Okay. So the last thing then is F. So F is the focal point or focal length. All right. And the focal length has the same sign convention. So F is positive if it's on the same side as S, and F is negative if it's on the opposite side as S. Okay? So F is positive if on same side. And then it's negative if it's on the opposite side. Okay. So that really sums it up. I think I've already kind of labeled R, but I'll leave it here. This is just the radius. Okay, so the important part is that R is always twice F. Okay, F, you can see it here, right? But those sign conventions will take some getting used to. We'll have plenty of practice with them. We'll use them again with thin lenses. So just definitely be aware of them, look them up, have your own way of making sure that they make sense and you memorize them. And then, obviously ask me any questions as they arise. Okay, so with that, I'm going to conclude the second video, and then we'll come back in a third video to show